Well, you all obviously know of Roger. I wonder how many of you know just how many fields Roger Penrose has contributed to. I spend my professional life talking to people who win Nobel Prizes and the rest. But I don't think I've ever come across someone who has contributed to so many fields. I mean, he worked with Stephen Hawking on singularities, and that led to our present theories of the universe starting from a singularity. He's contributed to our ideas of consciousness and the limits of logic and rationality, and has also done work on tiling the infinite plane. And a good guide for if you want to find Roger's work, look for where infinity crops up, and you'll find Roger at a little table nearby working on it. Roger, you've always been an extremely visual scientist. When did that start? Because you knew Escher and your father knew Escher. Did it come from that, or was it something?
Oh no. Well, my father was very artistic. He came. His brother was Roland Penrose, who was well known in surrealists. I mean, he was in with the surrealist group and was one of the founders of the Institute for Contemporary Arts. And he and those two and their brothers were all very artistic, and their father was a professional portrait painter. James Doyle Penrose. He used to do very sort of realistic sort of pictures, very religious pictures too.
Right, and then your father became friends with Escher, didn't he?
Well, the story is more complicated than that.
It always is with Roger.
See, when I was a graduate student in Cambridge, I went to the International Congress of Mathematicians, which was being held in Amsterdam. That was in my second year as a graduate student. And I heard about this exhibition by this extraordinary artist. They'd had an exhibition there because all the mathematicians around, they thought they would be interested in Escher. And it was one of the lecturers who, I saw he had a catalogue, and you opened it up, it's a picture of the birds flying both ways at once, night and day. But there were a lot of fantastic pictures there, and I came away thinking that I'd like to do something impossible myself. So I finally tried to draw pictures with bridges and railways and roads and things going in impossible ways, and I simplified this to a triangle, so that it's a triangle where each two edges meet at right angles, and it's impossible, but you can see the picture of it.
But I didn't know that you invented that.
I did, apart from it having been invented several years earlier by somebody else. But it wasn't quite the same. There's a man called Oscar Reuterswärd, who was a Swedish artist. He had a thing with cubes going around, which basically the same idea. You can trace back the idea to old pictures, Bruegels. I forget what they are. Yeah, there are.
And were you interested? Because, as I said, you've always been interested in infinity, or at least it crops up everywhere in your work. And of course, Escher's paintings, they often start off with a few simple shapes at the centre, and then a little bit further out, it's the same shape but smaller, and there's more of them. And then, obviously, as you get to the edge, if you could magnify it, there'd be an infinite number of them.
Oh yes, no, that was stimulated by somebody else. That was the Coxeter. There was another mathematician who was, well, call him a Canadian. I think he was Scottish originally. But anyway, he acquainted Escher with these pictures, what Escher called circle limits, where you have angels and devils, and they all get more and more crowded up to the edge. And the edge represents the infinity of the world that they inhabit. So these are...
But is that how important is the picture to your work? Because for someone like me who looks at it, it seems very important. Right. Why do you find pictures so useful? Because lots of your contemporaries, they're pure mathematics, and although you are a mathematician, it's unusual that you combine mathematics, but with pictures, that's how you, every time I've been to see you, and I can't understand, which is most of the time, he says, and then starts to draw a picture, at which point I still don't understand, but at least there's a picture.
Well, you see, when I went to University College as an undergraduate, and I was expecting when I went there I would find people who think like me, you see, because I was perhaps more mathematical than, there were a few other quite good mathematical people at school. But I thought, okay, they'll all be like me, you see. Well, I didn't expect to find so many different ways of thinking about mathematics. And one of the biggest divisions is whether you like to think visually or in terms of equations. And there were only about 2 of us in the whole class who preferred to think visually. So it's not so common in mathematics. The best mathematicians can do both, they can, well, I wouldn't say the best, a lot of the best can think that way. But it's kind of unusual. Well, you see, when it came to the exams, my best papers were not the geometry papers. My best paper was in algebra, curiously enough, because, you see, when you do a geometry problem, you have to see how to do it, and it's geometrical. And then you've got to translate that into words, and you write down the words. And you have to keep flipping back from one way of thinking to another way of thinking. So my view is that it doesn't really help in examinations. To be a visual thinker, it doesn't help you so much in exams. And so maybe that's a reason that mathematicians on the whole aren't as geometrical as you might think. I mean, certainly it's a minority of them who think that way.
Right. One of the other areas that you worked in is a small story that there was a competition some while ago, I can't remember how long ago, that amongst mathematicians. They decided, well, what's the minimum number of shapes that it will you can tile an infinite floor with? This is how they amuse themselves, I think. And at one point, and I know I'll get the details wrong, but I think it was a Chinese chap had it down to several thousand shapes. With
a student of his, yes.
Right, several thousand shapes. He could prove that you could tile an infinite space with this set number of tiles, and the pattern would never repeat. So it's not like a square tile. And then Roger got involved, because he thought, ooh, that sounds interesting. Would anyone like to guess how many shapes Roger has got it down to? Just shout out.
Say no,
yes, and everyone else went, oh.
Yes. Well, it worked its way down. I think it got down to about 100 by Robert Berger, who had the number originally. And then it got down to, kept working its way down till it got down to 6. Right. And I was aware of that 6. I had another way of doing it with 6, you see. But when I heard about that, and I was told that the chap who did this liked to find the smallest number, so I said, well, I can do it with 5, because I could glue 2 of my bits together. Well, it wasn't quite like that, but then I fiddled around and I got it down to 2.
And that was the end of that competition. But the interesting thing about it is, you think, well, that's an interesting pastime, but actually this work on aperiodic tiling has tremendous things to say about the limits of logic and the way that consciousness might work. And one of the things that's most interesting about your work is that Roger goes off in all these different directions, but are you thinking, this will give me another avenue back to this? Because your work has been tremendously varied, but it does sort of double back to things that you've always been preoccupied, like the limits of logic.
I don't know whether I can answer that question. I don't know. I just do what interests me mainly. And the logic thing, I had a lot of conversations when I was an undergraduate with Ian Percival. We used to talk about, well, a lot of other things, but logic was certainly one of the things we talked about. And I was very worried by this thing called Girdle's theorem, because it seemed to show that there were things in mathematics you couldn't prove. And then when I went to Cambridge as a graduate student, and I went to 3 lecture courses which were nothing to do with my actual work. One was by Herman Bondi on general relativity and cosmology. One was by Paul Dirac, famous quantum mechanics, one of the founders of quantum mechanics. And he gave, they were both beautiful sets of lectures in a completely different way. And then I went to another course, which was a course by a man called Steen on mathematical logic, because I was interested in this Girdle question. And I learned about Turing machines. Those are the general, the basis of modern computers, if you like, Turing machines. And I learned about Girdle's theorem. And I learnt, to my relief, that it was not that Girdle showed that there were things you couldn't prove. It's just that if you had a particular set of rules that you follow, and that these rules are things you could put on a computer to check whether they've been done right, then those rules, you can find some other example. Well, these rules prove things about numbers, you see, and infinite things. There you are, you see. Infinite things about numbers, such as, for example, every number is the sum of 4 square numbers, which is proved by Lagrange, quite a hard theorem. Or that every even number greater than 2 is the sum of 2 prime numbers. That's still unproved. Things of that sort, you see. These are statements about the infinite. Now the question is, you've got certain rules about how you prove things. And if you fix those rules, and if you believe they only give you truths, what Girdle does, he comes along and says, well, look, here's a statement of just the same kind, but what you could see, by virtue of understanding what the statement means, that you cannot prove it using those rules if you trust those rules to only give you truths. So if you're using the rules only give you true things, here's another thing which you can see is true by virtue of your knowledge that the rules only give you true things, but you cannot prove it using the rules. I mean, so it's twists of logic there. So you can tell it's true by knowing that the rules only give you truths, but you can't prove it using the rules.
Yes.
And I found that stunning, you see.
Yes.
Just absolutely stunning.
I mean, in case that's puzzling, that's the deep mathematical version of this statement is false.
Yes, but if that's...
you all understood it because you understand the rules
yes.
of the English language, but you can't decide whether what I said is true or not.
Yes, it has to be...
And it's not because I didn't say it properly or that you didn't understand it properly, and that's a trivial version, and Girdle...
Yes, but what Girdle really says, this statement is not provable by those rules.
Yes, but proved it. And is it? Would you agree that it basically made him the most unpopular logician ever?
Well, I hope not.
well, I'd say that if he taught at the University of Vienna, and if you go to the courtyard, the university there, big, huge building, and they have very proudly a bust in marble of every single famous professor, or every professor who taught there, going back several centuries, except for Kurt Gödel.
Well, that's a big mistake.
Yes.
Oh, gosh.
So...
I don't think they hate him, no. No, he opened up all sorts of things. He opened up huge areas of mathematics. No.
Yes, but he does pull the rug out from under the pretension
yes,
that you will
true.
have a formal system
yes.
which, once you've got it, will be able to give you the correct answer to any question you give it, which is still the founding belief that we'll be able to create an AI, and when we do, it'll give us the answer to everything.
Yeah,
Girdle rather clearly said, no, it won't.
Well, I mean, yeah, that's where it leads you. I mean, it shows you that's the way it led me, you see.
Yes. But that's made you quite unpopular too.
I have no idea. People disagree with me, that's
yes,
true.
Yes, they do.
I don't know. Well, quite a few bought my book, The Emperor's New Mind. So it can't be just unpopularity that did that.
Well, no, but I spent several months interviewing lots and lots of the techie boys who are doing the AI revolution, and if I mention your name, they go,
Yes, well, you see, it does show that there is something different going on I mean, this is what I learned from Steen's course. It may not have been quite how he put it, but there is something going on in human understanding which is not computational. That it's different from what a computer does. So, okay, when people call it artificial intelligence, I think that's a misnomer.
What
artificial
should it be?
Cleverness, perhaps.
Right.
But AC stands for alternating current, so you couldn't say that wouldn't work, you see.
Right, but how many people would you say, I know you don't like sides in this, but
how many agree with me?
But the fashion has run against you. The fashion is that, no, we're going to build a machine, and human consciousness is essentially, we will be able to capture it in a digital machine.
Yeah, well, I think that's just wrong. Yeah.
There, you heard it here first.
No, I mean, you can make it... Well, you said I did something else more recently. I produced a chess position, you see, which you give it to Fritz, tuned, that's the best chess computer system, you see, and you program it to be grandmaster level. And this is a chess position that you show it to any human player who knows anything about the game at all. It's obviously a drawn game. It's a draw. But if you give it to Fritz and play against Fritz, it loses.
Really?
Yeah. And I was expecting it to lose too.
You're a clever clogs, aren't you?
Well, not at chess. That's my. I was the chess dunce in my family.
And how do people react to this? That must have upset the group of people immensely.
Well, some people say, "Oh, I could program my computer to do that." But of course, that's cheating because you're using your understanding to. Well, I'm not sure. Wouldn't it be quite hard to I mean, you can do it to. I could program a computer to do the right thing in this position, but then you see, change it a little bit. Then I wouldn't. You see. Yeah. This position, you see, that's what I mean. He could program it to get the right answer for that position, sure.
But then, when you say there's something going on in human consciousness which is non-computational, it's quite an innocent-sounding sentence, really. But what word would you reach for to describe the thing which is not computational? Would you reach for something like intuition or inspiration?
Understanding.
Understanding.
Yeah.
But an understanding that you didn't get through by steps of logic.
Yeah, but you see, even that's not understanding, you're just following the rules. You see, if you simply follow the rules you've been given, you can do that without any understanding. The understanding is why the rules work. Right. And that's something different. Right. And that's why I say the Girdle thing shows you that if you know why these steps will give you only truths, if you've gone through that, that level of understanding allows you to transcend those rules themselves.
Yes, and that's something that Girdle and you and someone like Greg Chaitin have all said. The computer, once you've given it the rules, like the rules that they put into DeepMind or the program that beat Garry Kasparov, it can laboriously explore all permutations of that rules, but it can't jump outside the rules. And you're saying the human mind can, but not by having another rule that steps behind it to say, oh, now and again jump out of these rules, because you'd then be trapped in that larger set of rules. You'd still be trapped. And the interesting thing about Girdle is he spent the last 20 years of his life trying to prove intuition, and slowly starved himself to death. He went bonkers. But that's a rather interesting thing, isn't it? To want to prove that that intuition lies outside of proof.
Yeah, but I mean, you can get a long way with not understanding. I mean, that's what
I've got a long way without understanding anything.
Yes, but yeah. No, but you asked me what do I think it is. You see, that leads into another route. You see, I mean, this was the sort of reasoning that I was using. I mean, you know, although I was brought up in this Quaker family, as we were discussing earlier, I didn't have any religious beliefs, and so that even though I think there's something going on in our heads which transcends understanding and therefore is not a computer in the ordinary sense of the word, what could it be? Because we know that the laws of physics, I think we've had a wonderful example of that recently with these gravitational waves coming from black holes spiraling into each other, which this LIGO detector, it can tell because of enormous calculations that people have done on Einstein's theory. They know exactly what form these waves should be, and so therefore you can tell when the detector has actually received waves of that type. So this is an example which shows you how powerful you can imitate nature, how powerful you can imitate nature in this subject of Einstein's general relativity. Now you see, I asked myself, okay, what else? Well, there's quantum mechanics. You see, now quantum mechanics, it consists of two parts. You see, this is basically I learned from Dirac about the puzzles of quantum mechanics. I think it was partly because I dozed off at the beginning. It wasn't clear, my mind wandered at a certain point. This is his very first lecture.
You dozed off in Dirac's lecture?
No, I didn't doze off. My mind wandered. No, you see, it was right at the beginning, and he was talking about the superposition principle. So you see, if you have a particle, and if one state of the particle is it's here, and another state of the particle is it's here, then you can have states where it's here and here at the same time. Yeah. So you can see particles can be in two places at once. Crazy, but that's how quantum mechanics works. Then he took a piece of chalk, and I think he broke it in two, and said, look, the chalk is now imagined it's here and here at the same time. That was the point my mind wandered, you see. because he gave some explanation. I sort of had the faintest idea what it was. I just remembered something about the word energy coming into it, and I'm worried about that ever since, you see. So why is it that you don't have pieces of chalk in two places at once, or people in two places at once and all that? And this is a big problem in quantum mechanics. So my view was that quantum mechanics can't be quite right.
And Einstein had that view.
Yes, he had a similar view, yes. This is a little bit more specific because it has to do with why is it not right, but that took me longer to think about that. But the view is that it can't be quite right. And the way in which it's not quite right has to be taken advantage of by the brain. So this was the idea that I had, and I wrote this book, The Emperor's New Mind. I thought probably it would disappear without trace, but then Stephen Hawking had written his book on the brief history of time, and he had got, what's his name, Carl Sagan to write a foreword. So I thought I should get somebody decent to write a foreword, then maybe. So I got Martin Gardner. Right. So I had no idea what Martin Gardner's views were. He said, yes, I agree with you, he said. So he was happy to write a foreword, and then I thought, well, it probably won't disappear without trace.
No, the difference between the two books is that Brief History of Time by Hawking's about that big, and Roger's handy-dandy quick primer for consciousness is about that thick. It's got pictures.
That big. Yes.
But it's interesting.
It is true, a lot of people hated it, yes.
They did, oh gosh, yeah, because I was making a series on consciousness at the time, and again, my whole life has been mentioning you and people going like this.
Yeah.
Because the criticism was that all Roger has done is taken a mystery and wrapped it in an enigma and said, there you go. Taken two things we didn't understand and say, because we don't understand these two things, they must be the same thing.
That's not the argument at all. No, they hadn't read the book.
No, and none of them hadn't. That's true.
No, that's true. But the thing is, you see, I had no idea what the answer was. So I wrote the book thinking that by the time I had to learn some neurophysiology and that sort of thing, by the time I'd learnt that bit, I would see where there could be something going on in the brain. See, the argument had to be that it had to be some effect where gravity comes in. And I had no idea at that time. It didn't seem to be that nerve propagation had any chance of being the answer. And the thing is, you see, I was hoping that this book would be read by young people trying to learn about science and so on. Most of the letters I got from people were from old retired people. And those were the people who had time to read the book, I guess. But anyway, not just old retired people. One person who did read the book was Stuart Hameroff.
Yes.
And Stuart Hameroff, his day job is to put people, and maybe at the night too, and to put people to sleep reversibly. In other words, give them general anesthetics when they have operations. And unlike most of his colleagues who were just as capable of putting people to sleep and waking them up afterwards, they didn't seem to worry as much as he did about what they were actually doing.
Yeah.
So this point was, what do the general anesthetics act on? And his view was that they act on these things called microtubules. And so he sent me a letter and he said, well, the thing missing from your argument is you haven't mentioned microtubules. And I thought, microtubules? I get lots of letters from nutty people, you see. And I thought, oh gosh, it's another one. But then I looked it up and I saw that, yeah, they're real. I should have known about them. And these are little tiny tubes. And I thought the chance of preserving quantum coherence at that level was much, much greater than.
But also, in just the last year or two, a lot more people are coming round to this idea, because the problem was always people said, but can you maintain quantum states in the brain? Because the brain is a noisy, messy and warm place, which is generally not good for quantum mechanics. Generally, if we want to do anything with quantum mechanics, we buy a truckload of liquid nitrogen and freeze the entire place down, and then we start. Well, they. And so people didn't like it. But in the last 2 years, a lot of new people are starting, because they've realized actually they can find coherent quantum stuff in the brain where they didn't expect it. So Roger's detractors are all feeling a bit peeved at the moment. But are you a dualist? I mean, the reason I ask is because Roger has often said, there's the physical universe, but I think ideas and mathematics exist in their own dimension. Now, I'm maybe saying this wrongly, but if that is true, that is dualism. That's what ever since Descartes, you were not allowed to talk about. That there was something in the material universe, not supernatural.
Well, you see, John Searle used to accuse me of being a trialist. There were three worlds, you see.
Tell us
well,
what
I have
they
this
are,
picture
Roger.
with the three worlds. You see, one world I like to put at the top is the world of Platonic ideas, or specifically mathematics, which exists independently of us. And after all, since the universe was running along quite happily before there were people, the laws of physics were there a long time there were people, and so the mathematics which governs those laws was there quite independently of people. So that's the Platonic mathematical world, which has its own existence.
Has its own existence?
Yeah. And then the physical world is controlled by a small part of the mathematical world. And then when the physical world is in the right sort of construction, like human brains or brains of other animals, well, I don't know how far down it goes, but certainly not just humans, I would think, that when that's organized correctly, then mentality comes out of it in a sense. So it's as each comes out of the other, but then there's this sort of triangle, which is a kind of paradox, because the mathematical ideas can be directly accessed by the conscious thinking, so that it's a
So we
horizontal
would exist
triangle.
in two kinds of world at the same time. We exist in this world, but somehow our minds have access to this other dimension, which is non-physical. It's not a physical dimension.
I don't think of it as, to think of it as not physical is perhaps not the right way of thinking of it. It comes out, it's a different concept. You see, most of the things in the physical world don't seem to have awareness. And those things which do, somehow that you organize it correctly and then you get the awareness coming out of it. That's the sort of view I had. I mean, I think of them as it's not right to think of them as separate worlds. I don't think of it in the way that a dualist might, that there's a separate entity, which is the mind or something like that. It comes out of the operation of the physical world.
Okay. I mean, I don't think you'll get a scientist to say anything more inflammatory than that in the modern world. I really don't. In that case, ladies and gentlemen, would you join me in thanking Roger Penrose?
For more debates, talks and interviews, subscribe today to the Institute of Art and Ideas at IAI TV.